We're doing a stream. You should be notified. Clinical relevancy of metabolic acidosis can result in hyperkalemia. All right, just as a reminder, hyperkalemia means too much of that K plus stuff, the potassium. Potassium ions, too many of them. All right, so what happens is the proton gradient. So you inhale you oxygen, exhale carbon dioxide. If you have metabolic acidosis, that can result from like intestinal stuff, but it can also, like, an easy way to imagine it happening is when too much carbon dioxide is in your bloodstream. Because it dissolves as carbonic acid, which is acidic, and so you can have too many protons, and then in the bloodstream, and so it's going to want to penetrate tissues due to diffusion and thermodynamics. So excessive plasma concentration results in extrusion of extra potassium because the potassium is used to shuttle protons. Let's see. Somehow, I kind of forget. We'll look at that in a future card. And there's an electrically silent exchange of one proton because a hydrogen cation, a hydrogen cation is the same because a hydrogen is really just a proton. So if you lose an electron, hydrogen is a proton and electron, so if you lose your electron, then you're just a proton. With one potassium, the potassium uptake is therapeutically, acutely blank, right? So potassium is taken up by, triggered to take up by insulin, and so that'd be the sodium-potassium transporter, co-transporter, or antiporter, I suppose it is. And it is stimulated by insulin injection. Interesting. So uptake is therapeutically, acutely activated, increased, enhanced, good, close enough. We'll say 25 minutes. All right. So the next one on this list is potassium, and you can obviously see that that's true. When I have a card like this, and really this is just a result of the fact that when I generate when I use code to generate one of these from a tab separated list of values, and so I'll have like I'll have electrolyte, then tab cytoplasmic, tab extracellular, new line sodium, and so on. And so when I put that through, I don't always know if I'm going to have whether I'm going to have a header column and a header row, one or the other. So I just go ahead and sometimes I'll just leave the header row in there and make it assume that I have a header row, and then I just, when I'm using that particular version, I just always have to include a header row. But for the column, that's more inconsistent. So in the case where I have an really obvious entry in the column, in the rows, in the first column, what I'll do is I'll take that as an opportunity to memorize everything in that row. So in this instance, what I'm going to want to do is I'm going to say, okay, so let's see. So the potassium is relative to the the potassium concentration on the outside of the cell. So obviously the extracellular potassium is going to always be 1 times the potassium concentration on the outside of the cell. But the cytoplasmic in this one is 25 times. So I have to remember that I've got 25 times the concentration of sodium inside the cell, outside the cell, inside the cell. 25 times the potassium ion concentration outside the cell, inside the cell. Confusing way to say it. Okay. So I take the potassium concentration outside the cell, multiply by 25, and that's my concentration inside the cell. Okie dokie. Yes, and so if I want to, I can also take a little extra time, but I'm interested in thinking about this card a little bit more, and then I'll go through and I'll figure out what else is in here that I care about. One thing that I noticed, though, is that my negative does not look very superscripty in the HCO3, so I'm pretty sure that I put that in manually, so I bet it's correct. It's just the baseline is a little bit not as high as one might like it to be. And it probably has more to do with the fact that even though this the typical baseline shift, it's still in the midline of the baseline shift, and it doesn't go all the way up. So, and the numbers are larger, so they drop down further. So I think it's fine. Yes, I care too much about typography when I look at my cards. It's a little bit excessive. But as long as I use the rules, at least it'll be consistent, which is really the number one thing that I care about when I'm doing these things. I care about consistency, because anything inconsistent is noise, and noise distracts you from the process of of learning, or teaches you, you do learn, you end up learning, but you learn the wrong stuff. So I'd rather not do that. Although there is research that shows that expending a little effort when you're trying to learn something new actually enhances what you're already learning. So it's possible that by having inconsistencies in the formatting of the text, that can actually enhance learning experience, because you've got like, you unconsciously remember those little weird differences in the text alongside the factual information. So you end up with just like this garbage that actually helps you to recall or remember and recall important facts that you do want to remember, which is kind of like not very elegant or romantic, but it seems to be the way that it is, and nature is not always elegant and romantic. Although I suppose you could figure out a way to implement it romantically, like have like specific types of inconsistencies, the things that you do on purpose, and little jokes and things, and you know that's still not great. Like, it's the use of mnemonics, like the use of mnemonics, having to use mnemonics, like using mnemonics does not appeal to me, but they are extremely beneficial. Oh yes, potassium. I just did that. Sorry, I've activated my sketchpad here. Okay, again, we're losing power. Okay, main body fluid compartments. Right. Okay, so in these guys, man, the baseline looks bad. Anyway. Right. Okay, so protein in the plasma is about 7 grams per deciliter. What's funny about that, unexpected, is that in the interstitial space is 1 gram per deciliter. So that's kind of crazy. Let's see, plasma concentration. You can kind of see what's going on here, and you see the figure that this comes from. And let's make sure that there's not any important information. It looks like I've copied that out. Complex lipid bilayer with many transporters, carriers, pores, etc. Okay, great. The presence of solutes creates the osmolarity of the body fluids. Yes, osmolarity, number of free dissociative particles in the solution, and one molecular. So one osmol is one molecular weight of one non-polar, or no, non-ionized solute. So that basically means there's no formal charge on the whole thing. It could be polar, but whatever. I think if you have, yes, per solute, yes, then you have osmoles, and then you have osmolality, which is number of dissociative particles in solution per kilogram of H2O. Versus osmolarity, same thing. Let's see, yes, different number of particles outside, number, right. Yeah, well, they're both, right. Osmolality is, yes. And then if you have an ionized solute, then you could, it's not really a molecule, it's a salt. Salts are not really molecules, because they're not molecularly, they're just statically attracted. You know, it's not, you don't have a dynamic electron there. Like, to separate them, you just pull them apart. It's not like you have to alter the nature of an electron. You know what I mean? You don't have to break a pair of electrons, break a bond. So, in that sense, since you're not chemically altering it to pull it apart, it's not really a molecule. It's a couple of ions put together. It's a salt. Okay, so ECF, blah 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 blah. So right, so this is kind of a little bit ill-conceived because it's not really a relevant point, and it doesn't really so much have to do with the charge, but it says not ionized, so whatever. Cool, and we'll say one day. Look at it again tomorrow. Summary of Keys concepts. Right. So sometimes the last, let's see. First let's answer it, then we'll look at the source. Charges in the ion channels blank, or ion changes, right, in ion channels, leakiness, permeability, that's the word. Okay, so let's edit this card and have a look at how it works. Right, okay, cool. So that is actually the second. Let's see, resting potential is due primarily to potassium electric equilibrium potential. Right, how do you know that? That's why I didn't create a card. I've got like lots of cards that talk about that already. Let's see. For each individual species of electrolyte, their electrochemical equilibrium potential is controlled by concentration against any degree of permeability. Right. Yes, that's pretty obvious. Voltage equals potential, right? So that I just have to remember that. I mean, I know that the voltage is the electromotive force or the electric potential, but most of this is just kind of obvious stuff. It's important to also test yourself on the obvious stuff, though, because you do need to be loading relevant information into your brain for the exam. Even though, okay, so if they give you an open-ended question, most of the time, it can be difficult to answer certain questions, unless, even if you know the supporting information just as part of your background knowledge, if you don't associate it with the context of answering that question, you're not necessarily going to be able to apply it, because you can pull from everything you know, and come up with different answers that are rather plausible. Often because the question is written poorly, and there's not really one true answer. So instead, when you're answering exam questions, you have to answer it based on kind of your perception of what the answer should be in the context of the class. The fact that we have to do that is just an element of how poorly written exams are. And if you're the sort of person who relies more on their general knowledge to answer questions, you might be the sort of person who does a lot better on standardized tests than they do on school exams. It would make sense, because the standardized tests are kind of engineered to be. What I mean by better, though, is not, in some sense, standardized tests are easier, right? But on the flip side, standardized tests are also, you're also quantified relative to everybody else, so you get a percentile. So you might see, and also in college, you will be assigned a percentile on many of your exams too, on all of your exams probably. And sometimes you'll be allowed to see your percentile, so you can tell if you're doing better relative. Now that you are competing against a different pool of people, that is true. And you might be in a harder program than the program that most people are in. However, it's so there are flaws with making that comparison. But yeah. Anyway, but that's my hypothesis, and I'm going with it. All right, moving on. Permeability, bam, easy peasy. We're doing that in 4 days. We've got too many cards here to linger on a few of them. Cell membrane potential is controlled by degree of ion permeability and ion concentrations. Yes, okay, cool. Sodium channel by blah, blah, blah. Potassium. This is just all about potassium. 4 days, go away. Ovulation, 14 days in the menstrual cycle, is unrise of blood. Okay, so this one always confuses me, because it says, anyway, the answer is luteinizing hormone, or LH, but the answer is gonadotrophic hormone, luteinizing hormone, LH, right? But we know that there's also a hormone called gonadotropin that I think triggers the release of LH, which we could Google later. But, yeah, why not? Let's see. Yeah, let's look up gonadotropin. There we go. Gonadotropins. Oh, is it a sub? Oh, it's a category. Oh, it's a category. I say, let's check out Encyclopedia Britannica. I normally use Wikipedia, but I don't know, written by Robert Utiger. Alright, let's see. It'd be funny if people used Encyclopedia Britannica as a source for their Wikipedia articles. Let's see. Or maybe they consider it not authoritative enough, so it's not a valid citation. Let's see. Do they even have citations in, what the heck? Looks like they might not. That's crazy. Wikipedia won, Robert Utiger, or maybe the style guy didn't, well, that is neat. I like what this does, but, yeah, gonadotropin, one of several, hormones occurring in vertebrates that are secreted from the anterior pituitary gland. Adenohypophysis. No, that's the anterior pituitary gland that act on the gonad. Yeah, isn't that the, yeah, there are two parts of the pituitary gland. There's adenohypophysis and neurohypophysis. Neurohypophysis is, closely connected and related to the, hypothalamus. Anyway. Gonadotrophs, cells that constitute, they act on the gonads. Yes, luteinizing hormone is an example of a gonad. Yeah, well, that answers our question. Luteinizing hormone triggers the release of a single mature ovum, or egg from one of the ovaries. The egg travels down the uterine tube until it reaches the uterine cavity. An unfertilized egg is discharged through the vagina. I went it. Okay. Let's see. Plasma. Let's see. Sodium concentration of plasma. Oy. Okay, so this is the same as the other one, where we're looking at the concentrations. So remember they're saying that like 25, the concentration of potassium is 25 times what it is in the interstitium, in the intracellular fraction of the body water. Intracellular fluid. Okay, which it clearly is. Let's see, 25. Oh, it's 25. It's 25 times 525 minus 0.5. 25 times. Is that accurate? It's 24.5 times. That must have been an approximate by me. Let's see. 5 times 112.5. 27 would be closer. Shoot. Well, next time I get back to that note, I will correct it. Remember, this is one card, and one card comes from one note. But not one note, just one of my notes. Whatever, anyway. Plasma concentration. I do not recall. Basically the same as the interstitium, which makes sense. Ion channel types. Let's see. Voltage gated, the structure activated. What's the other one here? Ion channel types. Oh boy. I don't know. Anti-transport? No. It's a channel. Ion channel types. Ligand gated. Oh no. Oh no. That's a good example of that. Right. A ligand-gated channel has a selectivity filter. It has a ligand-binding receptor and a gate. The ligand-binding receptor opens the gate, pathway for the pore, or pathway for the ion, and then there's a selectivity filter to make sure the wrong thing doesn't get in. Electric field sensor. Yeah, well, isn't that the same as the selectivity filter, right? It's part of the same apparatus. It should be. Should be classified that way. Otherwise, what does the electric field sensor do? Perhaps it changes the shape. Oh, I know. The electric field sensor changes the shape of the pore of the channel as the ion enters it, and then there's a selectivity filter that decides whether it should changes shape all the way and let it go through, permit it to go through. That would make sense. Okay. Moving forward, we have 10 minutes. To measure volumes of specific compartments, right, use Evans blue or iodine-labeled albumin. Extracellular fraction X must not enter the cell but must equilibrate throughout the plasma and interstitial space. We use ribose? No. Glucose, a sugar which is, ribulose. Ribulose, maybe it's ribulose. I feel like that should be it. Let's see. What else would it be? Inulin. Yeah, that's right. We have ribulose. Inulin. So you do plasma volumes. Okay, so there are different ways to measure. So you do plasma volume. So you could like inject the plasma volume with 131 iodine labeled albumin or Evans blue, and then in addition to that, you could do the inulin. And so then you subtract the concentration of the inulin from the plasma volume, or the plasma volume from the inulin, and then that would give you plasma volume from the extracellular fraction. That will give you the extracellular. Yes, total body H2O must across the cell membrane freely and behave just like H2O. We use titrated H2O and heavy water, D2O. Yeah, so that's D2O, that'll go everywhere. Then total body H2O minus is intracellular, right? CP. That makes sense. So you just inject all three, and you get all three components. Fun, 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 fun. Moving, oh, nope, I did not get that right. Undo. 1 minute. Secondary active transport solute carriers. Sodium, potassium, ATPase. Glucose. What? Right, it's primary active. Oh, I see. Yes, I did in fact know that. I just forgot what I was looking for. Secondary active transporters use the ion concentration instead of using ATP directly. So the ATP generates the ion gradient, and then the secondary active transporter uses that ion gradient to then perform work, to then do work. Cell membrane potential is controlled by degree of ion permeability and ion concentrations. Ion distribution, large chemical gradients for potassium and sodium, are maintained by sodium-potassium ATPase active transport pumps. Potassium permeability of resting membrane is very large due to the open potassium channels in the membrane. Sodium permeability is much less. Membrane's resting potential of negative 90 millivolts is due primarily to the blank electrochemical equilibrium potential. Okay. Resting? Potassium electro, yes. Of course. Alright, tomorrow. Measure, right. Use inulin rather than, capillary wall. The blank arterial end of the capillary. Okay, so capillary wall barrier, right. Permeable membrane. There's two layers, which exchange occurs. Here only passive movement occurs, determined by chemical concentration gradients and physical pressures, hydrostatic and colloidosmotic or oncotic pressure, on either side of the capillary wall. Yes. So, let's see. The blank arterial end of the capillary is higher than the colloidosmotic. Okay, the hydrostatic pressure. In order to push it out, the oncotic pressure in the capillary. So water and solute is forced out into the interstitium, which is called filtration. Not excretion, infiltration. With forward flow of blood, PC, pressure, capillary pressure, falls at, is that capillary? We better fix this. Oops, I canceled before I look at that, yes. Right, well, no, I just said it. The, oncotic. Right. The hydrostatic, right? Yeah, blood pressure. Hydrostatic blood pressure, PC. I don't know why it's PC. Anyway, pressure of capillary, right? Well, whatever. I was going to subscript the C based on the answer, but I'm not sure. I guess that's why I didn't subscript it in the first place. With forward flow of blood, PC falls, and because fluid leaves the capillary, the impermeable plasma proteins become concentrated, and the okay. The pi C, which is the or P as you pronounce it, but then they're both PC. Okay, the pi is C, exceeds the PC. Pi C is the colloidosmotic. Okay. Oh man. Eventually the hydrostatic pressure is going to, oh yes, okay, that's the whole idea. So it filters when the hydrostatic pressure is higher, And as it filters out, two things happen. One, the pi c increases because the blood gets more concentrated. And then B, the hydrostatic pressure falls because there's more friction. And it fans out into more and more finer capillaries, presumably. So then it can reabsorb. Right? Right. So it can, yeah. Cool. The other thing that can happen is it can go into lymph. Pi c excludes the PC, refers fluid, reverse, blah, 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 interstitium, absorb. Over length of capillary filtration and reabsorption are approximately equal, so fluid does not accumulate in the interstitium. Right. However, if the pressure is too high, then you have pitting edema, presumably. So that could happen if you have hard this bumpy right. Not sure, because I thought that, anyway. Alright, 5 minutes. So 142, which is approximately the same. I'd be willing to accept 145. Reflection coefficient membrane permeability. Sodium chloride is, it's the standard? Impermeable. Okay, so reflection of, I guess, what you add. So if you add sodium chloride, it generates a sustained osmotic effect. No net movement of H. Why? Okay, well, yes. I mean, over time, it doesn't change. You enter it, you put it in, it doesn't go into the cells, and you'd pull out, and it would just stay the same, right? So no dynamic there, just static osmotic effect. No net movement of H2O. Okay. Glucose, on the other hand, does not have sustained. It drops off over time. So if you put in glucose, it's taken up by the cells with water. It's processed. Water stays. The glucose becomes carbon dioxide, FADH, NAD, more water, actually. ATP, all that good stuff. Because energy goes into those. Let's see. Glucose, impermeable, blah, blah, blah. Urea diffuses. Let's see. Glucose. Infused isoosmotic glucose, 300 milliosmoles per kilogram of H2O. Glucose is taken up, water follows, impermeable, right? And then blah, blah, whatever. Okay, major organs of the cardiovascular. Heart. I'd say the heart is probably one of those big ones. All right. Sodium chloride is confined to the ECF and determines the ECF volume. Yes. Hypotonic expansion, drinking water, both ECF and ICF fall on osmolarity, total blood. All right, only, let's see, isotonic expansion. Shoot. Right, okay, 300 million, because that's about, okay, I don't know, probably only plasma expansion. Right? Okay, and that is not probably, yeah, only ECF edit, right? Because the hydrostatic pressure. Alright, let's fix this. Let's see, sub. I do have to create more cards. Done. Check it. Oops. Why? Happy, happy, joy, joy. Save, please. Yes. Extracellular fluid. Yes. 5 minutes. Yeah, I know. Integrity, right? Integrity. Okay, 1 minute. Okay, ECF, extracellular fluid volume. X must not enter the cell, but must equilibrate throughout the plasma and interstitial space. We use inulin, a sugar which is foreign to the body. Also radio-labeled sodium or chloride, right? Because those are impermeable to the cells, in a sense. Although there are sodium leak channels, so ion channel types, ligand-gated. We've already gone over the anatomy of ligand-gated channel. Respiration, obtaining oxygen, characters of life. Digestion, yes, that is an important part of the life process. Contraction. Okay, well, hypotonic contraction would be the one remaining. Major organs. Lungs, maybe? No. Oh, larynx. No. Nares? Nose? Pharynx. I'm not sure. What's above sinuses? Nose? Nasal cavities. Sure. Yeah, nares. There we go. Yeah, it's not really cavities. Sinuses? Okay, fine. Okay, naval cavities before sinuses. Right. Okay. Only extracellular fluid. Isotopic exchange. Extracellular fraction, I suppose. 12 leg muscles are necessary to walk. Brain, spinal cord, motor neurons. Okay, hidden slide. Ooh, okay, example question. Question is, 45-year-old man has been ill for 24 hours. He weighs 100 kilograms. 24-hour fluid output measurements as follows. So he's lost a liter of urine. Okay. Which is like less than the normal 2.4. Right, so let's see. So he lost 200 millimoles per liter. Right, 1 liter is 220, or 200 millimoles. Sweat volume is 2 liters. Good God. See, I calculated this before, and I now forget how I calculated this. So I'd have to say, well, he lost. So he's down from his blood concentration. So he'd normally have about 2.4 liters of plasma. Let's see, 4 to 5% of his body. Let's see. So, how much does he weigh? 100 kilograms. So 60 kilograms is water. Let's see. Shoot. 1/3 of that, or 20 kilograms, is extracellular, including plasma. Let's see, 15 of that is interstitial. 5 of that is going to be his plasma. Originally had 300 milliosmoles. So 5, so you had 1,500 rounding, 1,550 milliosmoles of stuff. He's lost 200, 300 of those. So 1 liter's worth. Let's see. So he's currently at let's see. 1550 minus 300 is 1250. 1250 in 2 liters. It's not much. So what is the osmolarity? Let's see, 250 and 2 liters. Right, so that's easy. So 1250, so that's easy. So that'd be 1250, 625 per liter. It's like double what it should be. So that'll have to be spread out. So we're going to increase the pressure, we'll pull some out of the extracellular fluid, and the cells. Well, you know what? I am lost. So we're going to find out how they calculated that. Okay, initial 60% intracellular fraction rate. So, how did I do that? Let's see. Shouldn't that be? All right, so 60 kilograms, and then 1/3 would be intracellular. Oh, I thought. Wait, no, 2/3 would be intracellular. Right, 36. 140. One-third of 60 is 20, and 2/3 is 40. He weighs 100 kilograms. How is 24 40% of his total body weight? Okay, okay, this is stupid. I think this is supposed to be 70 kilograms. So then you calculate how many milliosmoles he has total. So then, let's see, so he's lost 3 liters. Let's see. And then how much has he lost? He's lost 600 milliosmoles. So minus 3 liters, 57 liters. Okay, you just automatically distribute it. Total osmotic particles at 24 hours, so you're down to 18. And then you say, okay, divided by 57, so 315 osmoles per liter, kilogram ratio, final osmotic concentration, osmotically active particles and ICFs, still the same. So the original one was 36 times, right? That. The new one is the new osmotic concentration. Let's see. Right, divided by whatever the new stuff is. Okay, so I don't think this is accurate because I think they assume 70 kilograms. It's 36 plus 24. Well, that is 40 plus is 60. I just don't know why they decided. It's frustrating. I just don't know why they decided to go with that. I'll have to watch the video. X34 is not 40%. So first they calculated all of the stuff in the body, all of the milliosmoles, the total number of milliosmoles in the body. Then and the total volume. They subtracted, came up with a new number of milliosmoles, come up with a new number for the, so fluid just moves continuously, and everything has the same osmotic potential, or whatever. Right now we're just going to assume that. So then what we do is we see, okay, that new concentration is going to be what the new osmolarity of the body is, the intracellular fraction. And the volume of the intracellular fraction is going to be reduced proportionally to the change. And so you're just going to divide 310 by 315. Let's see, 36 times 310 divided by, right, and then you can multiply it. So, anyway, it would not be a bad idea to put some latex in here. Here's some latex. I don't see a button for that, unfortunately. Well, anyway, moving on. Alright, give me a minute. I can't play it well. Alright, so it's time for break. Hope you guys are having more fun than I am. It's actually pretty good. It's just I'm tired. Okay, I'll see you guys after.